All right, so the second thing that I wanted to talk about is power transmitted by waves on a string. And it's pretty clear that since the waves contain energy and they move along, they're going to be transmitting power. There are a couple of different ways to calculate this. One way is to simply draw out your wave, y of x and t. Take a look at each individual point, and what you'll find, it has some kinetic energy because it moves up and down. So the kinetic energy is something like 1/2 the mass density times velocity squared. That's the kinetic energy per unit length. And similarly, this is the trickier part. There's the potential energy per unit length that is given simply by basically a restoring force. So it's like 1/2 times an effective spring constant, and here I won't derive that, times x squared, where this guy comes from the restoring force. It's related to the second derivative of the spring. So you can do that, and then what you would find is that the power has units of energy divided by time. So if you multiply this energy per unit length times velocity, length per unit time, that gives you your power. That's one way of doing it, and it gives you the right answer. But as I say, there's one little trick there, which is understanding what it means to have potential energy in a spring. Think of it as kind of a simple harmonic oscillator at each point, but it's a little tricky. So I'm going to go a slightly different route, which also gives the same answer, namely to ask where that energy comes from. So what we saw in class is that there's a very nice way of generating these traveling waves. So imagine I have a string doing something like this, and what I do is I attach it to a little hoop at the end, a massless hoop. The mass of that hoop is going to be 0. And that's then connected to some driver, let's say a spring, but it could just be anything that's driving that point up and down at a finite frequency. Okay, so there's some external force on that hoop applied by the drive, and that's what's going to cause waves to propagate through the medium. So we can ask, how much power do we have to drive this with? And the idea is, by energy conservation, the string itself does not have friction, so energy is conserved. Any power that I put into the left end is then going to get transmitted at the speed of sound, or sorry, the wave speed through the string. So this is going to be a way of calculating power. And in order to do that, what we really basically need to do is figure out what's happening to this hoop right here, this massless hoop. So, as always, we will start with Newton's laws. Here we have a hoop, and there are technically two forces acting on it. There's the drive force, which, if you're a little bit more careful than I've been, has both an x component, the external force in the x direction, and a y component, which I will draw as up. And then there's the tension in the string. So the tension in the string is coming off somewhere here. And quickly, we can figure out what is the direction of that tension in the string. So if I'm going to go ahead and redraw this, here's my hoop, and the string is coming off it like so. The tension force is simply going to be tangent to the point of contact. So the tension force is going to come off at this angle right here. Now that's good, because if we know the angle it comes off, you notice that that is related to the wave function. Here the string itself has y as a function of x at a particular value of t. This direction is related to the slope of the line. In particular, if I draw this out, if I draw some little piece of string right here, it has length delta x, height delta y, and the angle from the horizontal, theta, is right here. So a little bit of trig, tangent of theta is equal to delta y over delta x. And in the limit where delta x gets small, that's just the derivative. Here I'll write it as a partial derivative because it's a derivative with respect to x at fixed time. All right, so that's my angle theta that the tension acts at. Now I also need to break up F into components. So I can go ahead and do that, and it's a very similar drawing here, right? So my tension force F has two components. Let's call them Fx and Fy. We'll be interested in the y component. And what we see is that Fy is opposite the angle theta, so Fy is F sine theta. And while that's nice, it's kind of a pain in the butt because we have tangent here, sine here. So again, we're going to appeal to the fact that waves on a string have the property that the amplitude is much less than the wavelength, meaning that the angle at any given point, theta, is much less than 1. Let's go ahead and use this small angle approximation again. So for theta much less than 1, theta is approximately equal to sine of theta, is approximately equal to tangent of theta. They're all the same at first order. And so we say that the first derivative with respect to x is approximately theta and sine theta as well. So this is f times partial y partial x evaluated at the edge. So let's call the edge x equals to 0. All right, so we can actually plug into this equation. If we know the wave equation, y is equal to a cosine kx minus omega t. And the partial derivative with respect to x, as we've seen in class, was negative ak sine kx minus omega t. Which, when we evaluate it at x equals 0, is just positive ak sine omega t. All right? So that's my derivative. I plug that into my equation. I find that my tension force Fy is equal to Fak sine omega t. Good. So now we can go back to our free body diagram. There are two forces, this y component of tension and the y component of this external force, F external. Meaning that the total force in the y direction is the applied force, F external y, plus Fy of the string, the tension force, which is Fak sine omega t. I should maybe mention this is negative ak sine negative omega t. Sine negative omega t is negative sine omega t, so those negatives cancel out. That's why I get a positive number here. Okay, so this is all the forces acting on that little hoop. And you may remember that I said the hoop was massless. So F total is equal to mass times the acceleration of the hoop, which we know. It's actually the same as the acceleration of the string, but the mass of the hoop is 0, meaning these guys just have to add up to 0. So now if I solve for the external force, I bring this Fak sine omega t over to the other side, I find that the amount of force that I have to drive this guy with in order to make the oscillations happen is negative Fak sine omega t. So that's the driving force on the hoop. If I want to calculate the power that I have to apply, you may remember this formula. Power is simply force dotted into velocity. My velocity is entirely in the y direction. It's only moving up and down. So this is just F external y times velocity in the y direction. All right, so we now know F external y. Let's quickly figure out what's the velocity. Again, we've solved this. The velocity in the y direction is simply dy dt, evaluated at x equals 0, right, at this boundary point where we're doing all the motion. So we take a derivative, we get negative a omega sine kx minus omega t. I'm sorry, that was negative a times negative omega, so that's positive a omega, sine of kx minus omega t. When I evaluate x equals 0, this guy goes away, and sine of negative omega t is negative sine omega t. So in other words, this is negative a omega sine of omega t at the boundary. All right, so I have the velocity, I have the force. When I plug them in together, I get that the external power is equal to negative Fak sine omega t times negative a omega sine omega t Negatives cancel each other out. I can combine some terms. I have f a squared omega k sine squared omega t. And then just one more step, since we want to get this in the language of f and mu for the string, I want to get rid of k. So what I'm going to notice is that the velocity of waves in the string is simply omega divided by k. And I know for a string that that is the square root of f divided by mu. Okay, so if I want to solve for k, I bring k over to the other side, divide through by root mu over f. I get that k is equal to omega times the square root of mu divided by f. And finally, when I plug this guy in to my external power equation, I get that power is f a squared omega times omega root mu over f sine squared omega t. And finally, after a teeny bit of algebra, canceling out that f in the denominator, I get the promised expression, square root of mu f a squared omega squared sine squared omega t. So this is what I wrote in class. You again notice that it is time dependent when t goes through 0. So in other words, when the cosine is at its maximum value. That will actually correspond to 0 power. But when it goes through equilibrium, which is when the sine is maximal, that sine squared will be equal to 1. So the power goes between 0 and square root mu f a squared omega squared. The average power is simply given by averaging the sine squared, which is 1/2. Okay, so that's all I wanted to talk about in this little extra calculus after hours. Thank you for listening. Have a great week.